so we can learn from each other. Our presentation today is MATLAB coding in civil engineering research. And actually, it's not only about MATLAB, it's like in general about coding. And I am speaking about MATLAB because this is what I do have experience with. But I believe that coding in general in civil engineering is really important and helpful, very helpful, based actually in your research area as well. So why I believe, and actually this is actually my opinion, why it is important to use some coding tools in research. I believe first is like to reduce the time consumption, because in research we do a lot of iteration and iterative stuff. Like you have some data, you need to process this data, you need to have some plots. And with all of these iterations, you consume a lot of time, or we consume a lot of time. And also, this when you have more iteration, I believe we will have more errors. So I believe with coding, you can reduce the time and reduce the error as well. And also, when we consider if you are doing some parametric study, here it became very important actually to use some coding, because actually with coding you can actually, it's very easy to increase your parameters. And when you increase your parameters, you are likely to get more efficient results. And also you can get like more firm or solid conclusions. And if you are trying to publish a journal paper, for example, it is very important to convince the reviewer that you did an sufficient amount of work. And the more you increase your parameter study, or the more you increase your iterations, the more you will be able to convince the reviewer that you did a good job in your publication, and it can be accepted. And the outline I will be going through with you today is, first thing is data processing. And in this data processing, actually, I'm going to provide 3 examples, which I'm using. I used coding to make the data processing and reading the recording file easier. And then I will have second point is automated analysis. In this automated analysis, we used Matlab and SAP 2000, and it does not need to be Matlab and SAP. It can be Matlab with any other analysis software, but this analysis software should allow the user from using coding parameter with it. So you can use it with SAP 2000. You can use it, I think, with Abacus and ANSYS. MyDAS does not have this tool yet, so you cannot use coding with MyDAS. But by 2021 you would have it. And the last point we have is automated model updating. Let's start with our first point, data processing. So, and again, in this data processing, I will be providing 3 examples. The first example with us is this Excel file. And this Excel file has about 36,000 rows by 24 columns. And actually the issue is this Excel file was not the size of the file itself, but it was more about the data. We need some data from this file, and we need to get this data like quicker, and we wanted also less errors. And this data actually contains the loading configurations for 81 trains. We were working with a railroad company here in the United States, and they provided us with this loading configuration. So this company are able of measuring the train loading configurations. And when we say loading configurations, we mean it can give you how many cars in this train and the wheel spacing for this train, and also the load of each wheel. And we wanted actually to get the loading configuration for each train. And this was very difficult to use Excel. And when I say difficult to use Excel, actually, I tried first to work with Excel, but it was not really possible for me. And I was only able to get data for maybe 6 trains because of the time consumption. And it was really tough. But then when we started doing coding, we can easily do maybe 3 or 4 lines of coding that can read this train's loading configuration, and it can give you the loading configurations for each train, and you get like these such plots. That's the one shown here to the right. This figure actually shows the number of the cars for each train. The top one is like by time, like for first time, how many cars, second time. The second one is sorted from smaller number to the highest number. And the most important thing for us as a structural engineer or bridge engineer are loads. So we can also get what are the maximum axle load and the minimum axle load for each train. And the top figure here shows the one in blue. It shows the maximum axle load, and the one in the bottom shows the minimum axle load for each train. So this was the first example. If you move to the example number 2, this actually is a monitoring system. And again, here I'm trying to highlight why using coding may be very useful, and actually not using coding may make research is really difficult, and you will not get the data that you hope to get. So this actually monitoring system, I will start describing what it is first. So here we have this bridge, and for this bridge we install the monitoring system. And monitoring systems means a measurement system that you install on this bridge and then you leave it. But you can access this monitoring system results from your office. For example, this bridge was located maybe 150 miles from my office back to the university, but I was able to access the data that this system is measuring on a daily basis, or on whenever I want to access it through the internet. So simply, we have here for this bridge, we had about 24 strain sensors, and each 4 of these strain sensors are connected to this white box. And actually, this white box, we call it a node. So this node will be connected, each node is connected to 4 sensors. And this node will be connected to the computer system that's shown in the figure here to the left. This computer system is actually this white box here. It has a computer. This computer will record the strain measurements when a train crosses a bridge. And we have here finally these 2 solar panels that use to power up the system. And for each train passage, what's going to happen? This computer will start recording the data when the train crosses the bridge. When the train leaves the bridge, it will not record the data. So we call it event recording. Event recording meaning collecting the data when we have train, do not collect the data when we don't have a train. So let's back to our coding thing. So for each day, we find that we have about 55. 55 means we have on average about 50 trains that cross that bridge. So this means actually after about 9 days, almost 2 months, we have almost 3,000 measurement files. So and actually imagine we need to access these data on maybe daily basis, weekly basis, something like this. We need to compare the results. So actually, and imagining that we need to open this every day, we need to open 50 files manually, I mean, and then look into this data. I don't think it's something easy, but then again, we develop a code that can read all of these data, and then we can start again comparing the results of all of these files at one time. So again, it was not possible with Excel, but it can be easy with coding. So this figure, it may not look good, but the one to the top left shows actually comparison between about 1,500 strains, but this actually at one location only. So this, and then we start processing the data. This is a good thing when you have coding. You start actually processing the data, meaning eliminate the trains signal or the strain signals that you don't like. And actually, this is what we did exactly. So we have here 1400 train. Then we start processing, okay, eliminating this train. I didn't like the signals of that strain. So we eliminate those unwanted trains. It dropped to about 500. Then more processing of the data. You get about 170. And then more processing with the data. You get about 100. And we actually, at the end, we use this 100 out of the 3000 train. We use this actually because the strain signals are very close to each other, and this is actually what we wanted to use. And is this only an example how, this is only an example how coding can make the life easier when you have like huge amount of data like this. Then example number 3, this was actually a lab test. It was not as big problem as the previous 2 actually. And for this lab test, we have here like, we have this stringer. Here is about 100-foot span. 100-foot span, I think, is about 30 meters, I believe so. Or so 100, and then we have here like this a loading system here, and we have another loading system here, and we apply loads using this yellow pressure. We call it pressure cells. And this beam actually here, we call it a spreader, is a double cantilever. So whatever load that we're applying here at the end of this cantilever, it will be only one applied load at this point load. So this point load will be the point of load application. And then for this system, actually, we have for this testing, we have 2 measurement systems, 2 different measurement systems, I mean. So for each test, we had 3 different recording files. And this test was planned to have about 100 test runs. So we have 103 for each. We have about 300 files for testing. And back to the point when I told we have 2 different systems. Why do we have 2 different systems? Because actually here we're using 2 different sensors. We have here this one we call it, it's very famous, it's called BDI sensors. These BDI sensors are reusable, so we can use it multiple times, and they are very expensive. So when we install sensor in this system, we make sure that these sensors are very far from the point of failure, because we don't want this sensor to get damaged. And close to the point of failure, we use another sensor. It's a foil sensors that are cheaper, and they can be used only once. And because of that, we have 2 different systems. We have systems that report the recording for BDI sensors, and we have systems that recording or reporting the recording for these 2 other sensors, loads and strains. And again, with Excel, it was not really easy, but then we did some coding that can automate the process. So for each test, actually, we need only to put the recording file, and then the code will read each file, and it will combine the data together, and we will be able to compare these results. And actually, this is like a comparison between the vertical displacement and horizontal displacement for 3 different test runs. And I mentioned before, it's a total of 100 runs. And at the end of the day, also, we were able to combine all of these files at one Excel file. So using coding, actually, you can read Excel file and you can write an Excel file. With that, the first 3 example for data processing is done. Now, I will be moving with automated analysis using Matlab and SAP 2000 Open Application Programming Interface, OAPI. And we will start with iterative analysis. And what meant by iterative analysis is we need to change something in the model. So we have model using any analysis software. We need to change some parameter in that model. For example, we need to change the model's velocity. I would like to change the end condition. Instead of having hinged and roller, I need to use springs, for example. And this spring might have different stiffness. This example about changing the model parameters. And also, iterative analysis could be changing the load. As we mentioned earlier, we have 81 train configuration, and at some point, we wanted to model this 81 trains configuration. And for each one of these iterations, we need the results. We need to run the analysis and get the results. So for this actually bridge that's shown here to the right in this picture, it was a repeated bridge that we want to do some iterative analysis for it. And actually, manually, it was really tough to do that. And when I started this analysis manually, I was trying always to limit the number of iterations. Because when you do stuff manually, it is very time consuming, a lot of errors, and again, it will be less effective at the end. But because of the time consumption, you need to reduce the number of iterations as possible. But when I start manually, I figured out, okay, my results were not good. So I need to increase the number of iterations. And to increase the number of iterations, I cannot do this manually. So I had to learn like Matlab coding at this point. Then the objective from this study, actually, for this shown bridge, was to develop a damage detection framework. But why we wanted the damage detection framework for this bridge? This bridge is a riveted truss bridge, and it was constructed, I think, 1910, very old bridge. And if we took a look about this bridge components, like this picture shows the bridge from underneath. So we have this horizontal element, we call it floor beam, and we have this element we call stringer. And there's the major problem with these bridges here is the connection between the stringer and the floor beam. This connection at the beginning, people assume it is bent. Bend means it does not have any bending moment. So the bending moment at the end of this stringer here is 0. However, after doing a lot of research and field measurements, their research realized that this connection has significant end moment. And because of that, this connection has a lot of problems with fatigue. And fatigue problems can be in two things. So this picture here, actually, it's two pictures, one to the right, one to the left. It shows the problem with this kind of connections, stringer to floor beam. So it can be either vertical crack, and this caused by fatigue, or it can be like a broken bolts. Both of them could happen for this connection. And this is a major issue for this type of bridges. So we want actually to develop a structural health monitoring system that can predict if we have damage or not. And the predict means we can apply the monitoring system that we showed earlier, and then we process the data of this monitoring system, and then it can give us alert. Okay, your bridge is good, or your bridge have a problem, or your bridge has a problem, or your bridge has a damage. So this was the end goal or the objective of this project. So we started this process actually analytically, and this is what we are focusing on today. And then we did some field validation as well. Moving again, when we do iterative analysis, we need to change something in the model, and we need to change the load as well. Let's focus first on the model parameters. For this bridge that we showed earlier, this show a plan view of the floor system, and here we have the truss elements, and we have here the interior horizontal lines or elements show the stringers, and the vertical elements show the floor beams. And we can see here that there is highlighted numbers with yellow. This actually is the assumed location of damage, and you can see we assume that we have damage at the stringer to floor beam connection at 20 location. So we wanted to change the model parameters in our SAB model at 20 location. And for each time we have only one damage at one location at a time. Besides the damage location, also we have another parameter, which is damage intensity. Damage intensity meaning the magnitude of the damage at each location. For example, in our model, we'll start first assuming all of these connections are healthy. Healthy meaning we don't have any damage. We will run the model, and then we will get the results. This is the first one. Then I will start at connection number 1. I will model a damage intensity of 10%. Then run the model, get the results. Then moving to the next point, apply a damage at connection number 1 with a 20% damage intensity and up to 100%. After finishing connection number 1, I will assume again number 1 is a healthy connection, and then I will move to connection number 2. And again, 10% damage, 20% damage, up to 100%. Then until I approach the connection number 20. So this is how we wanted to do with our model. This is the first thing, which is the model parameters. Besides the model parameters, we wanted also to change the loads. So we mentioned earlier we have 81 trains loading configuration provided. Then we sorted actually these trains based on the load. And we figured out we have here about 24 trains that have the highest load magnitude. And we selected in our study actually to focus on this high load train because we assume high load trains will give us close agreement. With that, we highlighted what we want to do in our model, like in two things, parameters and loading. Now, after changing each load and each model parameters, we need to run the analysis. And this picture actually shows the 3D view of the model that we developed. And we used the Matlab code actually and SAP Open Application Programming Interface to run all of these parameters and loading and run the analysis. Now, let's move what Matlab coding is going to do for us. Before we go to the next point, sorry, if we did simple calculation, we realize that considering the 20 location damage and 10 different damage intensity and 24 trains, we'll have about 5,000 analysis or 4,800 exactly analysis run, which is very difficult to do this manually. And moving to the next point, what Matlab is going to do. The very thing Matlab is going to do, it will read the Excel file that has the 81 trains, and it would be able to select the 24 trains that we wanted, or it can select whatever trains that you select, that you would like to select. After that, Matlab will control SAP 2000. So it will start taking the trains from the Excel file, and then it would model these trains in the Excel and the SAP, and then it will modify the connections, like first the location, second the intensity, run the analysis, and extract the results. And at the end, Matlab will give you a matrix that have the 4,800 analysis results run. After that, you can start, after getting your results, you can start doing your research. So actually, Matlab coding or any coding is only a tool that make getting the results easier. It's not the end goal. After getting the results, you can do your research. For us, we use like machine learning to be able to predict the damage location and damage intensity. And actually, this one show a heat map. We call it heat map. It's a plan view of the bridge that show here. This thick exterior elements are the truss, and the interior horizontal lines are the stringers. And we have the vertical elements here that shows the floor beam. And this one show actually this red point shows that we have damage here, and this another plan view shows that we have damage at another location. But this only like the way, anyway, you can select for highlighting the damage location or intensity. With that, we finish the second point in this presentation. And now I will be moving to the last point, which is automated model updating. And what we mean by automated model updating, here, some people call it model calibration. Like in easier way, when we go to field, we take some measurements and we usually develop analytical model to the bridge, or it does not also to be a bridge, can be a building. And then we need to match, or we would like to have our model give us the same results as the measured responses. And here it came the meaning of model calibration or model updating. We need to change our model so that it can predict that the same results that we are getting from the field. And I should say it does not need to be the same, but it should be close. And you may never get the same results, but close results. And actually, this figure here is not a really good picture, but this is like a plain Girder bridge. I think the depth of this one was about 10 foot, meaning about 3 meters. So, and the picture to the left here, it shows the 3D model of that bridge that we use SAP 2000 again. And here the two elements at the end, at the exterior ends, are the main girders. And again, this was a blade girder bridge. Riveted mean it's composed from multiple blades. It is not like something with one blade at the top, one blade at the bottom. No, it's multiple blades riveted together. And again, we have here the blue elements are the stringers, and the green ones are the floor beams. And this plan view actually show a plan view for the bridge with the accelerometers that we installed. We had 12 accelerometers installed at these marked red points, and we were able to measure acceleration in the horizontal direction and in the vertical direction. Then initial results. Initial results meaning what we get from the field and what we get from our initial model. Initial model means the model without doing any calibration or any updating. So we took from the field the acceleration measurements, and then we use software called Artemis. It's very famous software, and this software you feed it with the measured acceleration, and it will be able to give you what are the frequencies and what are the mode shape of this bridge. And with that software and measured responses, and also with that layout of acceleration measurement, we were able to identify 3 major mode shapes. This is called like stabilization diagram, and here we can see the frequency, and we were able to get, we have like 3 frequencies. First one is 5.17 hertz, second one 9.36, third one is 14.5. And if we take a quick look about the comparison between the measured responses and the initial model results, it can be shown here in this table. So we have here the first column shows the mode number 1, 2, 3, and then here we have the field, and the second column is the model or the initial model results. And I think that the important column is the very last one, which is highlighted here in green, which shows actually the difference between the updated, the original model or the initial model, and the field. We can see for the first mode we have about 20%, about 2% or minus 2%. Actually, the ratio here actually is very good. Actually, we can tell that this model for the first mode does not need any updating. It's good. But if we take a look for mode number 2 and mode number 3, we can see that we have 23% difference, and for number 3 we have 10% difference. Based on that, we need to do some model updating or calibration to improve our model so that we have less difference between both. And actually, to do model updating, first we need to do some requirements. The first requirement is model updating parameters. And what's meant by parameters is like what should we change in our model. For example, you can change the model's velocity. You can change the fixity ratio of the connection. You can change the rigidity of the members. You can change the end condition, like instead of using pin roller, you can use springs. And actually, this is usually based on the experience. So I have seen in some research, people may use 1 or 2 updating parameters in their model. And I have seen some people using 31 parameters. So, and again, when you increase the number of parameters, you may get better results, but it will need more work. And the second thing we need to take care of is the objective function. And in easier way, what's the objective function? It's only a function that has the difference between measured responses and the analytical model responses. So it's only like frequency of your model minus the frequency of your field experiment. And when this objective function, or when the difference between both reduced, you are getting good model. If it is very high, your model is not good enough. Then let's move to our work. What did we select as our updating parameters, or what we select to change in our model to improve it so that the results from our model will match the results from the field? The first thing we selected is the models of elasticity, which is E. And this actually was based on research. Some people, we found research that told or stated that for these old structures, you may have a difference in the modulus of elasticity about plus or minus 20%. And then the second thing is the stringer, again, connections that's highlighted, marked here in red. This connection is related connection, and it is not fully fixed and it is not fully bent. So we start playing with the fixity ratio of this connection. And also for the floor beam and the main girder, we change the bending stiffness. This actually main girder, I think it had about 4 plates. And at some point, these plates may not work together. So if they not work together, actually this girder will have less or smaller stiffness that is assumed. So we assumed also, like, we can change the main girder bending stiffness. Based on these assumptions, we need also to give like an indication about the limit, because when the coding starts, it will need like a range in which we need to apply or select your parameters value. So we define like here for the updating parameters, we have like lower bound and upper bound. Lower bound means the minimum value that the code will not go below, and the upper bound is the upper values that the code will not go above. And this very necessary is this, like these values are very necessary for the iterative approach that the code is going to use. Then moving to our objective function, we need this objective function to be minimized, meaning close to 0. And actually this equation shows the objective function we used. Some people actually call it a residual. Any name is fine. So, but the most important thing, it is like the field experimental frequency minus the frequency of the analysis divided by the experimental frequency. You can change this. It does not have to be this way, but it should be something close to that. So, and as we can see, if this value approaches 0, this means actually the experimental value are very close to the analysis value. And we should consider actually each one of these is a vector, so it's not one value, because for the experimental, we have 3 values, 5, 1, and I think the last one is about 12. So it's vector minus vector divided by a vector. It's not one value. And when these residual or objective function approaches 0, this means actually the field frequencies are almost like the model frequencies. Then moving to next important thing was that we use genetic algorithm. This is like very famous algorithm that can do optimization. Optimization meaning it can select the parameters, the values of the parameters, and define them and try to minimize the objective function. So this algorithm will do some iteration until it finds the best values for your updating parameters that we selected, that includes the model's velocity and the bending stiffness, until it finds the lowest minimum possible objective function. Let's go how this thing works in our case. In Matlab coding, first we define the genetic algorithm. This genetic algorithm will select an initial value of our updating parameters. And then Matlab will define these initial values in our submodel. And then it will run the analysis. Then it will get our mode shapes and mode the frequencies. And after getting these results, it will calculate the objective function. And based on this objective function value, it will start or it will move to the next point of iteration. So this process will be repeated until the lowest minimum possible objective function approach. In each time, actually, this genetic algorithm, based on the calculated objective function, it will select the new values for the updating parameters, model them in the set, get new results. But it's very important that this objective function will select the values between the limits that we defined earlier. And then after doing that, it was almost about 5,000 iterations for this genetic algorithm to get the best results for us. And it is very important to mention that actually these updating parameters are very important, because actually if you change the updating parameter limits, your values may change. After doing that work, we have this table again, but in this table we added a new column that shows that these two columns that highlighted in red, it shows actually the percent difference in our updated model compared to the original difference in the model that was initial one. We can see for the first mode, actually we were not able to get better than the initial value, but we can see for the second mode, it dropped from 23% to 2%. And for the third mode, it dropped from difference 10% to 3%. With these actually minimum values of differences, we agreed that these values are good and enough, meaning that this model is good enough. The final thing that we need to use is the final parameters. Final parameters mean what are the parameters that give us these very low ratios. And actually this table shows what are the final parameters that if we define in SAP 2000, it will give us like the final results that are close enough to our model. Finally, I think I have this video that shows the right side one show actually the mode shape that we get from Artemis based on the failed iteration, and the left side show the mode shape that we get from SAP 2000. And both of them are a torsion mode, but both of them are in a very good agreement with each other. With this slide, we finished actually our three main parts in this presentation. Then moving to our quick conclusion. I think coding can help in expanding the parameter work, and it's very easy when you do coding to expand the number of parameters or the number of root cases. And based on that, when you have a huge parameter set and huge results set, you can get better conclusion. And with that, actually, it is very easier for a researcher to convince the reviewer about his or her work. Because if you have less parameters, less results, some reviewer actually even will not read your entire work. Mainly, reviewer will look at your abstract and conclusion and maybe very early introduction. And based on that, he or she will decide to go more or further with your publications or not. And coding, I think, can reduce the time consumptions, and it can reduce also the human error. I think all of this presentation focused only on coding and research, but actually coding also can be used in design. And I'm not sure if anyone of you is like focused on design as well or not, but the same optimization procedures that we do in research are really needed in design. Because, for example, I used to work in both tension bridges, and for me, it was really difficult to find what is the eccentricity of the cable and what is the area of the cable and the profile of the cable, because for both tensioning, we need to define eccentricity at every location. And this actually requires a lot of iterations in the work. And with huge amount of iteration, usually you will not be able to keep tracking of all of these changes. But I think with simple code lines, you can increase the number of iteration for such work and still keep the record of all of these and get better optimized design work. That also is better to convince your client and the reviewer of your work. And with this, I think I finished my presentation, and I would be happy if anyone have any question. And thank you.
Thank you very much, Dr. Ahmed. And now it's time for question. If anyone have question related to the topic, please feel free to open your mic and ask your question. Okay, if there is no question, I have a question from my side. I'm asking about the parameters you choose for updating the model. Why this parameter especially selected for updating?
Actually, the parameter usually is based on experience, okay? But if you need a better way to select the parameters, again, you need to do some people call it sensitivity analysis. So in sensitivity analysis, you can put whatever parameters in your mind, okay? And for example, I selected to change the modulus of elasticity, okay? So you will do a separate study by changing only the modulus of elasticity, and then get the results for all of these iterations. And based on the results, you will decide if your modulus of elasticity is good or not. You get my point? So you can do some sensitivity analysis for each parameter you think of. But in general, these parameters mainly based on experience. So there is no firm way that tell you you have to use this parameter or you have to use this parameter. But the best way actually is to do sensitivity analysis. You can consider, for example, 15 parameters and do sensitivity analysis. You may be end okay using only 10 because these 10 parameters are more efficient in your case.
We need like more clarification about the coding part between the interaction between SAP and Matlab. And also I want to ask, can we do this with another programming language like Python or something else?
You can actually, if you go to SAP itself, it has coding example for using Visual Basic, using Matlab, using Python, and I think it has also C#. So we can use it with multiple coding language. But the problem is always, let me share something with you. I'm not sure if you will be able to see it or not, but I will try to share something. I have a problem actually with this one. Actually, I had a code, but I'm not being able to see it. I don't know why. But let me try again. But actually, I can send you the Matlab, like the Matlab coding I did in this research, and actually you can use it if you like. And if you have any question, I would be happy. Actually, you can email me. It's not a problem. Okay. Can you see this one?
Yes, it's clear now.
Okay, so actually, this how we figured out what what the coding line would do in MATLAB. For example, if you like to open a MATLAB if you would like to open SAP 2000 using MATLAB, this is actually the 2 lines that you need to use. If you use two lines, it will open your model. For example, if you need to assign material properties, okay, if you follow actually this highlighted line, for example, of the coding, will do this. Will define the name of the material. It will define modulus velocity, Poisson ratio, and thermal expansion, and so on. So I have something like this I can share with you. If you need to assign frame element property, meaning if you would like to have cross-section area, shear area, torsion area, anything of that. So this coding line, actually, I try to do something that can help people to see the connection between the coding and the SAP windows that they are familiar with. The rule actually for SAP 2000, it does not give you full examples for everything. You need to find it your way. But I will be happy to share any of these codings that I developed before. If anyone needs them, I can send all of them to you. And actually, they already published. So if you go to my page on Scholar, you can download, but I can send them to you. It's not a problem here.
Okay, thank you very much for sharing this with me. Of course, if you can send this like this tutorial, I think it's like something like tutorial to.
I can send it to you. I can.
SAP. Yeah, but so if we have like, options to use like different language, different programming language, why you choose MATLAB exactly?
Actually, this is what we had in the university, and this is what everyone has experience with. And actually, MATLAB has a lot of functions that's already can be used. Okay, not like Python or C#. So it has actually a lot of functions that's ready for you to use, but with other language, you may need to develop these functions. So it's more easier, I would say.
Okay, we have question.
Okay.
We have a question. I think, Doctor, can you share the simple flow of formulation using MATLAB? Maybe started from governing equation up to optimization.
Can you ask again? I didn't get that question really.
The question again, Doctor, can you share the simple flow of formulation using MATLAB? Maybe started from governing equation up to optimization.
Okay, you need my presentation again, right?
They want you to share the simple flow formulation using MATLAB. Maybe started from the governing equation up to the optimization.
I don't know what's simple flow. Sorry for that.
I think they just need like the model, how
okay.
we start, like something like hierarchy, how to, like what's the steps we need to do, starting from the choosing the governing equation up to the relationship between MATLAB and SAP and how to get the result.
Okay, so you need like me to send you like the coding I did or something like this?
I think maybe we can arrange a second session about this.
Okay. I don't mind if anyone like to use MATLAB coding. I can help him if you like.
Yes, we can arrange like a small session about like this one after this. Maybe more focused about how to use this coding.
Sure, but if people have questions, it will guide me to be prepared for them.
Yeah, of course. So I don't have any other question. If anyone else have any question, please open your mic, ask, or send your mic on the chat, question on the chat.
Yes, please.
Hello, go on.
Dr. Ahmed.
Yeah, assalamu alaikum.
Yes, assalamu alaikum. This is Ahmed Rageh from Al-Azhar University. Hello, Dr. Ahmed. Hello, Dr. Mahmoud. Hello, everybody. May I ask one question, please?
Sure.
Sure, yes.
Yeah, of course.
Yes. Which confidential ratio we put it as a data to judge the model. It means
Which one?
confidential ratio. 90%, 95%, which the certified level, you can say this model is calibrated well.
Actually, maybe up to 5% is good, but you may find this ratio actually is different from one to another. So there is no firm ratio that can tell you it should be 2% or it should be 5%. But for research, you cannot go to 10%. You're always trying to have something less than 5%.
Yes, okay, I get you.
And also, if you have, for example, the example I gave, it has 3 different modes. It was not one. And for the 3 of them, I have less than 3%. So if you have only one parameters or one mode shape, I think you will be shooting or trying to get something about 2% or something. So it's also depending on how much parameters or values you are comparing or considering.
Yes, this moves us to the second question.
Sure.
Is it possible to make a few points through the model to monitor the results?
You can do what? Some points through the model to do what?
Monitor do calibration.
I think I cannot hear your voice very well. If you can raise it up.
Okay. I'm trying to say, can we put some points at different locations through the model to specify the ratio of confidential? Let's say it is the right of the model 50%, it is the left of the model 55%, in the center of the model 60%, like that.
You can do whatever you want. If you are doing something like this, you can do that for sure. But like you should have some reason where you are changing these values. You get my point? But
yes.
I don't think anyone, if you ask like question how much should be the difference, is 20% or 5%, I don't think there is a firm answer for that. Especially when you are dealing with measured responses. Okay, it's very difficult actually to get everything matches.
Yes. Thanks. Thank you very much, Dr. Ahmed.
You are welcome.
Yeah, thank you.
So, do we have any other questions? So, we have a question. This question. Thanks, doctor, for the lecture. Can an analysis procedure by fully automated to analyze incoming live stream data and produce result to client with none of the human interaction required using Matlab and SAP 2000?
I didn't do that before, but if you know to do this, how to do this in SAP, you can do it with Matlab.
Anything can be done. Anything can be done on SAP can be done on Matlab via Matlab.
Yes, but you may spend some time. Actually, is a PDF file I have just shown. I spend a lot of time to find what are the coding lines that matches the Matlab functions. Okay, because these are not listed in SAP on SAP website. So you need to spend some time only to see how to write the code to control SAP. There are some functions there, but not everything is there.
Yeah, I see.
Is this answers the question?
Yes, I think so. We have any other questions from the attendants? Okay, I think by this question we can end the question and answer session, and we are very happy. We are very pleased with this very rich session from Dr. Ahmed, and of course we are happy to mention that this session will be recorded and uploaded to our PGSCE website, Facebook page. and maybe also the PGSC YouTube channel. And we will ask Dr. Ahmed to share the slides with us, the paper with the introduction to the Matlab and SAP, and all will be shared on our Facebook page. Thank you, Dr. Ahmed, for this rich session.
Thank you
for attending this session, and I declare the end of this session. Thank you, everyone.
Thank you. Have a good day.